Similar to the ratio test is another test called the root test. It works under a different mechanic and therefore applies better to different types of series, but it has the same general conclusion where we're going to look at a limit as n goes to infinity, and if that limit is small enough, then the series will converge. So we will again start with a sequence of positive terms. And this time, we're going to do the limit as n approaches infinity of the nth root of the nth term of the sequence. So when n is 1, it would be, well, simply a to the n, a sub n itself. But when n is 2, it would be the square root of the term. When n is 3, it would be the cube root of the term. When n is 4, it would be the fourth root of the fourth term, and then the fifth root of the fifth term, and the sixth root of the sixth term, and so on. This applies very well to series that have an exponential component to them, because the nth root will cancel out the nth power. It has the same conclusions as the ratio test in that if L is less than 1, the series converges. If L is equal to 1, including infinity, if L is greater than 1, including infinity, then the series diverges. And lastly, that if L is equal to 1, the test is inconclusive. The idea behind this is that a series with an exponential component will, of course, grow and grow and grow. Very often, there will be something that tamps it down. Again, it would need something else to work with it in order to help it the terms of the series continue to shrink. If the nth root of the terms shows that the tamping aspect of it, the thing that tamps it down and keeps the terms shrinking, is powerful enough, then it will keep the terms getting smaller fast enough to allow the series to converge. For example, suppose we have the series with the rational function 3n plus 1 over 5n minus 2 raised to the n. Now, this certainly would be incredibly difficult to do with the integral test because it is a rational function raised to a variable power. This would be very difficult to integrate. Likewise, the direct comparison test and the limit comparison test do not necessarily provide us with an obvious comparison series. The ratio test would be very difficult to work with here because of the n's inside the rational expression as well as the exponent. This actually is a very good time for the root test. So we would do the limit as n approaches infinity of the nth root of the nth term of the series, 3n plus 1 over 5n minus 2 raised to the n. And of course, the idea here is that the nth root exactly cancels out the nth power and leaves us with the limit as n goes to infinity of the rational expression 3n plus 1 over 5n minus 2. And this is actually very easy to deal with, again, through L'Hopital's rule, or through multiplying numerator and denominator by 1 over n, or simply the fact that both are degree 1 polynomials, so it should approach the ratio of the lead coefficients. This is a value less than 1, and therefore, by the root test, this converges. Now, this may not be the most obvious thing, so it might help to, again, list out some of the terms of the series to get a feel for what's going on here. So starting with n equals 1, the numerator would be 3 plus 1 is 4. The denominator would be 5 minus 2 is 3, and that would be raised to the first power, giving us the first term being 4/3. For the second term, we would have 3 times 2 is 6, plus 1 is 7 in the numerator, over 5 times 2 is 10, minus 2 is 8 in the denominator, and then that would be squared, giving us 49 over 64. Now, this is definitely a smaller term than what we see before, because 4/3 is bigger than 1, and 49 over 64 is smaller than 1. For the third term of the series, we would have 10 for the numerator and 13 for the denominator, this time raised to the third power. And that, of course, is going to get quite disgusting. 13 cubed is 2,197, while 10 cubed is 1,000. So this is now smaller than 1/2. We're going to take one more step here, because obviously with it going to the fourth power, this is going to continue to get out of hand. But the numerator now would be 13, and the denominator 18, and this would be now raised to the fourth power. 13 to the fourth power is 28,561, and 18 to the fourth power is 104,976. We are now down to something approaching 1/4. So perhaps it would be easier to look at these in terms of decimals to see how the terms are dropping to 0. 4/3 is, of course, 1.3 repeating. 49 over 64 is 0.7656, etc. 1,000 over 2,197 is 0.455, etc. And 28,561 divided by 104,976 is 0.272, etc. So what we can see is that these terms are dropping, and noticeably so. It would not be surprising to find that these terms actually do converge, or they obviously approach 0, but it would not be surprising to find that the sum actually converges to something finite, because the terms are approaching 0 and they are dropping fairly quickly. Let us look at another example where the root test will show divergence. This time, we will look at the series 2 to the n over n squared. Now, this is similar to a series that we used as an example in the ratio test, where it was 3 to the n over n cubed. So again, this series could be done fairly easily with the ratio test, but we're going to use the root test here to show that there is the possibility that multiple tests may apply. So the root test would have us do the limit as n approaches infinity of the nth root of 2 to the n over n squared. The square root would apply to, the nth root would apply separately to the numerator and denominator, which would help us because in the numerator, we can get some simplification. In the denominator, we are not going to be so lucky. In the numerator, the nth root and the nth power cancel out and leave us with simply a 2. Now, the difficulty with the denominator is in not being clear exactly how this is going to work, because the base in the n squared is growing, but the index of the radical is also growing, and that's not exactly clear. What I'm going to do here is take the nth root and write it instead as an exponent of 1 over n, so that I can combine those two exponents to give me n to the 2 over n. Now, by properties of limits, we can do the limit of the numerator separately from the limit of the denominator, which is helpful because the limit of the numerator is, of course, quite easy. But in the denominator now, we can focus on just that n to the 2 over n. So the numerator is going to result in a 2. We're now going to pull the limit in the denominator out because we're going to have to do some manipulation of this in order to evaluate the limit. Namely, a technique that we saw with L'Hopital's rule, we're going to have to do e raised to the limit as n approaches infinity of the natural log of n to the 2 over n, which will, of course, become e to the limit as n goes to infinity of 2 over n times the natural log of n. This can be further rewritten as e to the limit as n approaches infinity of 2 ln of n over n, which, of course, approaches infinity in the top and bottom, and therefore would require L'Hopital's rule. So we would have e to the limit as n approaches infinity of the derivative of 2 ln of n over the derivative of n. The derivative of 2 times ln of n is 2 over n, and the derivative of n is 1. So the numerator of this will approach 0 while the denominator approaches 1, and therefore we have e to the 0, which is 1. That is the denominator up here, so that the overall limit is equal to 2. That is bigger than 1. By the ratio test, or the root test rather, this then diverges. We can again get a feel for this by looking at the terms of the series. When n is 1, we have 2 over 1. When n is 2, we have 2 squared over 2 squared. When n is 3, we have 2 cubed over 3 squared. Then 2 to the 4th over 4 squared. Then 2 to the 5th over 5 squared. Then 2 to the 6th over 6 squared, and we can see that the numerator is definitely growing considerably faster than the denominator is. Therefore, these terms are growing, and by the divergence test, this series would certainly diverge. And that's what the root test is showing, that the terms are still growing at such a rate that even the nth radical, even with the radical increasing in index, it's still not enough to show that the terms shrink quickly enough for the series to approach 0. In fact, the terms don't shrink at all, which is why we can see that the ratio of the limit came out to be bigger than 1.